Okay, so this section is 6.4, exponential growth and decay. Just a review from Algebra 2. If we have an exponential function, y equals a times b to the x, remember the x only applies to the b, not the a, using order of operations. And if b is greater than 1, then the function represents exponential growth. Remember that exponential growth looks something like this. So this is growth. And if b is between 0 and 1, then the function represents exponential decay. And remember, decay looks something like this. Again, we learned this in Algebra 2. You can review that if you need to. What we're really going to do in this section is look at a variety of different word problems and how we're going to use differential equations to solve those problems. We're going to start out with a very easy type of differential equation called separable differential equations. A separable differential equation. A differential equation of the form dy dx equals some function of y times another function of g is called separable. What we're going to do is separate the variables by writing 1 over f of y dy equals g of x dx. Basically, all I'm doing is I'm taking the dx and multiplying it over to the right, and I'm taking the f of y and dividing it over to the other side. Then from there, what we're going to do is actually integrate both sides. We'll integrate the left side with respect to y. We'll integrate the right side with respect to g, or with respect to x, and then we'll be able to find the solution to this separable differential equation. So let's look at an example. We want to solve dy dx equals x over y. So our first step, of course, we are going to take the dx and multiply it over to the right, and take the y and multiply that over to the right. So doing that, we now have y times dy is equal to x times dx. So now I have two differentials. What we're going to do is just integrate both sides. Now the integral of y with respect to y, we're going to add 1 and divide by the new number, so that is 1/2 y squared equals 1/2 x squared plus a constant. I only have to add a constant on one side because adding one constant is the same as adding two constants. We would just put them together. So now what we need to do is solve this equation for y. So what I'm going to do is multiply both sides by 2. Notice that I don't actually have to write 2c because 2 times a constant is still just a constant. It hasn't changed anything. So now what we need to do is square root both sides. So then y is equal to the square root of x squared plus c. And so that's very nice, but let's assume that they give us an initial condition. Let's say they give us that when x is 1, y is 2. So we're just going to do the same thing that we've done before. We replace y with 2 and x with 1. So let's square both sides, which tells us that c is equal to 3. So my equation now is the y equals the square root of x squared plus 3. Okay. All right, let's look at the example dy dx equals cosine x e to the y plus sine x. The y plus sine x is all in the exponent. So the first thing that I want to do is break up that exponential. So we're going to write this as dy dx equals cosine x e to the y times e to the sine x. Remember, when you're adding the exponent, that's the same thing as multiplying the base. So now what we're going to do is we're going to take our e to the y and divide that over, and we're going to take the dx and multiply that to the right side. So what we end up with is 1 over e to the y dy is equal to cosine x e to the sine x dx. Now, since we have a differential on both sides of the equation, we can simply integrate both sides. I'm going to rewrite the left side as the integral of e to the negative y dy equals the integral of cosine x e to the sine x dx. Now, technically, you need to use substitution for both of these, but we've done a lot of practice with this, so you should kind of have this down. E to the negative y dy, the integral of that would be negative e to the negative y, equals the integral of cosine x e to the sine x dx is just e to the sine of x, and we'll add in our constant. Note that the derivative of e to the sine x would be e to the sine x times the derivative of sine, which is cosine. But we're not finished. We still need to solve for y. So what we're going to do is multiply both sides by -1. So e to the negative y equals, let's write this as, we'll make that a step, negative e to the sine x minus c. Now technically I can leave this as a plus c. Because it's just a constant, we don't know what it is yet. It doesn't matter if it's positive or negative, because when we solve for that later on, it'll adjust itself. Let's go ahead and rewrite this. E to the negative y equals c minus e to the sine x. And just to make it a little prettier, I said sine of x. All right, now to undo an exponent like that, we're going to have to take the natural log of both sides. You should remember that from Algebra 2. So we're taking the natural log of both sides of this equation. So then we have negative y equals the natural log of c minus e to the sine of x. So finishing it up, let's just divide by -1 again. We get that y, our function, is equal to the negative natural log of c minus e to the sine of x. So this is our general solution, right, because it contains just a constant, a variable. So let's go ahead and simplify this a little bit more, using, of course, our initial value that they gave us. So we have 0 equals the negative natural log of c minus e to the sine of 0. Now, of course, sine of 0 is 0. E to the 0 is just 1. So we have 0 equals the negative natural log of c minus 1. And to solve for c, now remember that there's really a little tiny base e here. E. So what we're going to do is e to the 0 equals c minus 1. The negative could have just divided over in this case, so we don't need to pay any attention to that. E to the 0 is, of course, 1 equals c minus 1. Add 1 to the other side, so 2 is equal to c. So then our final equation, our particular solution, is that y is equal to the negative natural log of 2 minus e to the sine of x. That's it. Let's look at another example. All right, so let's look at the example dy dx equals y plus 5 times x minus 2. Why don't you guys take a moment, pause the video, and try this one yourself. I'll go ahead and put the solution up so that you guys can see how it works out, but I'd like you to try this one yourself before moving on. All right, so to do this, we start by dividing both sides by y plus 5 and multiplying both sides by dx. Then we're going to integrate both sides. The left side will be integrated with respect to y, and the right side will be integrated with respect to x. So then what we have over here on the left side, we're going to need to do some u substitution. We're going to choose u to equal y plus 5. Then du is equal to just 1 dy, because the derivative of y is just 1, since we're taking the derivative with respect to y. So then we really have the integral of 1 over u du, which we know is the natural log of u. So then what our problem has become is we have the natural log of y plus 5 is equal to the integral of x is 1/2 x squared minus the integral of 2 is 2x plus some constant c. Now, of course, we need to solve this thing for y. So what we're going to do is remember, just like in the last example, this is a base e, so we can rewrite this in exponential form as e to the this whole polynomial equals y plus 5. I'm just going to change the left a little bit. This is the same thing as e to the x squared over 2 minus 2x times e to the c, which is the same thing as just some other constant, equals y plus 5. I'm going to ignore the absolute values for just a moment here. I can do that because e to the anything is always a positive number, and adding 5 just makes that more positive. So we're not quite done. All we're going to need to do is subtract that 5 from both sides. So we have c, move that in front, e to the x squared over 2 minus 2x is equal to y. Let's go ahead and give ourselves an initial condition to work with here. Let's look at the point 0, 1. So when x is 0 and y is 1, let's go ahead and try to find that c value. So we have e to the 0 squared over 2 minus 2 times 0 times our constant has to equal 1. Well, this is the exponent here is just 0. 0 minus 0 is 0. And e to the 0 is just 1. So we get that c is equal to 1. So that being said, our particular solution now is y equals, I lost my minus 5, didn't I? I sure did. Oh my goodness, I'm so sorry, guys. I subtracted 5 over from this step right here, so there should have been a minus 5 here, a minus 5 here, which changes our c value because we have c minus 5 equals 1, which means that c actually needed to equal 6 from adding the 5 over to both sides. I apologize for that. That's what happens when I'm doing this late at night. So what you're going to do now is we have 6 e to the x squared over 2 minus 2x minus a whole 5 as our particular solution. Alright, so let's start talking about why we need these separable differential equations. We're going to first talk about the law of exponential change. You guys have done enough exponential growth and decay problems that you have started to notice that the amount of something that you start with makes a difference in the general outcome. Like if you think about a bank account that's continuously compounding, if it starts out with a lot of money, you're going to earn money a lot faster than if that account started out with just a little bit of money. That's just the way that exponential growth works. So what we're going to do is we say that dy dx, the rate of growth, right, dy dx, is equal to k times y, where k is the growth constant if it's positive, or the decay constant if it's negative. So let's write that down. K is greater than 0 implies growth, because that's positive. K is less than 0 implies decay, because that's negative. All right. So let's go ahead and use our separable differential equations to solve this equation. I'm going to multiply both sides by dx and divide both sides by the y. So then we have 1 over y dy is equal to k times dx. K is just a constant, remember, representing our growth or decay. So now we're going to integrate both sides, the left side with respect to y, the right side with respect to x. On the left, the integral of 1 over y would be the natural log of y, equals the integral of k would just be kx plus some constant. Okay, we need to solve for y. So what we're going to do is remember that that natural log has a base of e. So we're going to rewrite this as e to the kx plus c is equal to y. Again, e to the anything is positive, so I no longer need to worry about those absolute values. I'm going to do the same trick that I did earlier. Remember, when we're adding the exponent, that's the same thing as multiplying the base. So this would be the same thing as e to the kx plus e to the c. E to the c is just another constant, so let's write that as capital C e to the kx equals y. Now, if we are looking at this as some sort of function of time, instead of using x's, let's go ahead and use t's. So we're going to replace the x's with t's. And just to make it more clear that it's a function of time. So then we would have y is equal to c e to the kt. Now at time 0, let's say we just have y naught, some initial value for y. We don't know what it is. We just want a nice particular solution that we can use over and over again to demonstrate this exponential change. So when I plug in 0 for t, because now this is a point t comma y, we get that y naught is equal to c e to the k times 0. Well, k times 0 is just 0, and e to the 0 is just 1, and c times 1 is c. So y naught is equal to c. I can replace my c with y naught. So we get the equation that y is equal to y naught e to the kt. Does this look familiar to anyone? It should. This is the same equation as a equals p e to the rt that we learned in Algebra 1 and Algebra 2. So again, your y naught, or your principal, that's your starting amount, how much you had to begin with. K, our book uses K, some books use R, that's your rate of growth. If it's bigger than 0, it's growth. If it's less than, that should just been a 0 up there. If it's less than 0, that is decay. And of course, T is your time. So we have just derived how the equation A equals PE to the RT came about. Of course, A equals PE to the RT only works for continuously compounded interest. If we have something that's compounded on discrete intervals, like monthly or quarterly or even by the minute, then we need to use this equation. A of t is equal to a naught times 1 plus r over k to the kt. So let's look at how this works. So let's say we're investing $800 at 6.3% for 8 years. We want to know how much is going to be in the account if A, it's compounded continuously, and B, if it's compounded quarterly. Again, this is an Algebra 2 problem. There's actually no calculus in this problem. It's just now you know where that compounded continuously equation comes from. So let's look at this. For A, it would be the amount in the account after 8 years is equal to the initial amount times e to the r. We need to write it in terms of a decimal, so it's 0.063 times 8 years. When we do that, we get that there will be $1,324.26. For part B, compounded quarterly, what we're going to do is the amount in the account after 8 years is equal to the initial amount times 1 plus the rate, 0.063, divided by k, which is how many times it's broken up. So in this case, it would be 4. Quarterly is 4 times a year. Raised to the kt, which in this case was 8. So doing that, following your order of operations, you get $1,319.07. So clearly the continuously compounded formula works in your favor. However, it's not drastic. It's about $5. Nothing to really write home about after 8 whole years. However, you can imagine this is just $800. If we were to make this $8,000 or $80,000, these two equations would be yield significantly different results. Let's look at another example of what separable differential equations are used for. One of the reasons that we use separable differential equations is to solve problems about radioactivity. In general, we can use the differential equation dy dt equals negative ky to represent the decay of radioactive materials. Of course, y is how much material you have, and k is just the rate of decay. In these problems, we're going to define k to be greater than 0. So the way that this works, to solve this differential equation, we're going to divide both sides by y and multiply by dt. So then, of course, we would have the integral of 1 over y dy equals negative k dt. And we've already solved one very similar to this. And going through and doing this, we would get y equals y naught e to the negative kt. Of course, y naught is the initial amount of material that you would have, radioactive material. So what we want to do is find some sort of equation that would tell us how to find the half-life of a material based only on our decay amount. So let's say we only know K, which is pretty easy to find. We know the K for our radioactive element, and we would like to figure out how long it takes for that material, the amount of that material to be cut in half. So we're looking for its half-life. So what we want is the end amount, the amount that we end up with, to be half of what we started with. So we're going to say that 1/2 of y naught is our ending amount. We want that to be equal to y naught e to the negative kt. So let's solve this equation. This is just algebra 2. We're going to start by dividing both sides by y naught. So then 1/2 is equal to e to the negative kt. Let's take the natural log of both sides. The natural log of 1/2 is equal to negative kt. Now, if you recall, 1 over 2, that's the same thing as 2 to the negative 1. Okay. But another one of our logarithm rules is that if I have an exponent, I can multiply that down in front. So negative natural log of 2 is equal to negative kt, which means that the natural log of 2 is equal to kt. So we want this in terms of t, so I'm going to go ahead and divide both sides by, or we want it in terms of k, so we're going to divide both sides by k. I'm sorry, my k's sometimes look like one less thans. So we have that the natural log of 2 over k is equal to t. So what this does is it tells us that based on our k, we will always be able to figure out how long a half-life is. So let's look at an example of that. Scientists who use carbon-14 dating use 5,700 years for its half-life. Find the age of a sample for which 10% of the radioactive nuclei originally present have decayed. So if 10% has decayed, that means 90% still remains. So we have 90% of the original amount, so 90% of A naught, is equal to A naught times 1/2 raised to the t over 5,700. Now let's talk about why we did what we did. The 1/2 is there because that's how long it takes for the 5,700 years cuts the sample in half. We're dividing t by 5,700 because we want to figure out how many times in our amount of time our sample has been cut in half. So if our time was 5,700 years, then 5,700 over 5,700 would be 1. 1/2 to the 1 is just 1/2. So we would be left with half of the original amount. So we're looking for that proportion. Right now, we have everything we need in this equation to solve for t. So let's go ahead and do that. First, let's divide both sides by A naught. And then what we're going to do, we have 0.9 equals 1/2 raised to the t over 5,700. Now we're going to need to take the log of both sides. The question is, what kind of a log are we going to take? You could get fancy taking logs with different bases, or we can just stick to what we can do with our calculator and just take the natural log of both sides. So the natural log of 0.9 is equal to the natural log of 1/2 to the t over 5,700. Now, of course, one of our log rules is that we can take the exponent and multiply that down in front. So now we have that the natural log of 0.9 is equal to t over 5,700 times the natural log of 1/2. So really what we're left to do is multiply by 5,700 and divide by the natural log of 1/2. So what we know is that t is equal to the natural log of 0.9 divided by the natural log of 0.5, 1/2. And then, of course, we multiplied by 5,700. So we're multiplying that by 5,700. We plug that into our calculators, and we're going to get that t is approximately 866 years. So the sample that we found was 866 years when 90% of the radioactive nuclei is still remaining. All right, so we have one more type of problem that we're going to look at, which is actually called Newton's law of cooling. All right, so Newton's law of cooling. You guys all know that if you have like a cup of hot tea and you put it outside, eventually it will cool to the temperature of the surrounding area. Well, the rate that it cools depends on a couple of things. It depends on how warm the temperature was to begin with, as well as how warm the surrounding temperatures are outside. That'll affect the rate at which something cools. So we're going to let capital T be the temperature of an object at some time lowercase t. And then capital T sub s will be the surrounding temperature. We're going to say that the rate that the temperature changes with respect to time is equal to negative k times T minus Ts. So the change, the difference between the temperature of the object and the temperature of the surrounding area. Well, we know that that dt, the change in temperature, that's exactly T minus T sub s, right? Because the change in the temperature, you're just going to take how much it started at, and eventually it'll get down to the surrounding temperature. So the change in temperature is just the difference between those. So what I'm going to do is take this equation and write it as a separable equation. So I'm going to write this as dt minus Ts dt is equal to negative k T minus T sub s. So solving this separable differential equation, we see that we get T minus T sub s is equal to T naught minus T sub s e to the negative k t. Just doing the same thing that we've been doing over and over. By dividing it over, integrating both sides, we would have 1 over t minus t sub s, which would give us the natural log, raise both sides to the e, and so on. This thing right here, the t minus ts equals t naught minus ts times e to the negative kt, is known as Newton's law of cooling. So let's look at one example of this. Okay, so here's our last example for this lecture. Let's say we have a hard-boiled egg and it's 98 degrees Celsius. It's dropped into 18 degrees Celsius water to cool down. After about 5 minutes, or let's say exactly 5 minutes, the egg is 38 degrees. How long until the egg is 20 degrees? So until it's edible. So let's use the rule that we just learned, Newton's law of cooling. T minus T sub s equals T naught minus T sub s e to the negative kt. We know that T sub s is equal to 18. That's the temperature of the water. We also know that T naught, the starting temperature of the egg was 98 degrees. And we know that this change in temperature occurred when T was 38 when little t was equal to 5. So that gives us a value right there. All right, so let's just plug all of this information in. And what it should leave us with is just k as a variable. So what we have is 38 minus 18 equals 98 minus 18 e to the negative k times 5. So let's simplify this. We have 38 minus 18 is 20 equals 98 minus 18, 80 e to the negative 5k. Divide both sides by 80. I'm going to start working over here. That gives us 1/4. 20 divided by 80 is 1/4 equals e to the negative 5k. Well, let's take the natural log of both sides. So the natural log of 1/4 equals the natural log of e to the negative 5k, which is just negative 5k. Then the natural log of 1/4, remember, 1/4 is the same thing as 4 to the negative 1. The natural log of 4 to the negative 1 is the negative natural log of 4 equals negative 5k, or the natural log of 4 equals 5k, because the negatives divide out. So that tells us that k is equal to the natural log of 4 divided by 5. So what does this mean? This tells us that we can write an equation that the temperature of the egg is equal to 18 plus 80 e to the negative the natural log of 4 over 5 times t. So now we have an equation for the temperature based on however long the egg has been in the water. So let's see how long it takes for the temperature to get to 20. That was our end goal, was to get to 20 degrees. So what we're going to do is replace the big T with 20. We want to know when does 20 equal 18 plus 80 e to the negative natural log of 4 divided by 5 t. So you can solve this algebraically, or you could graph this. If you wanted to graph it in your graphing calculator, you would make this y1. This whole nasty equation would be y2, and then you would just simply find where they intersect. Or you could solve it algebraically. It is possible. You would subtract 18, divide by 80, take the natural log of both sides, divide by the negative natural log of 4 over 5, and then you would be able to solve for t. When you do so, you get that t is equal to 13.3. So that's how long it takes from time 0 to get to 20 degrees. But the question asked how much longer will it take to reach 20 degrees. So it's already been in there for 5 minutes. So let's go ahead and subtract the 5 minutes it's already been in there. It's going to take 8.3 more minutes to reach that 20 degrees so that it's edible. All right, we are going to start class next time with an example about Newton's law of cooling. I'll give you the equation and everything. We're just going to practice with it a bit more. Have a good evening. I'll see you soon.